acceleration of body 2, right? You can see it. The same thing with Atwood's machine, right? If M2 is accelerating downward very quickly, right, then mass 1 will be accelerating upward at the same rate. And the same thing in this problem here, okay? So this is like Atwood's machine light, which is why I'm going to work this one out, and I will leave Atwood's machine for you to solve, because there's not that many of these dynamics problems that I can come up with that are interesting, and this is probably one of the more interesting ones that's not overly burdened with complexities.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, so lecture 33 is on statics. Statics, what does that mean exactly? What does the word static mean to you?
Still.
Still, not changing, right? So in a static situation, the sum of the forces, sum of the external forces, is equal to 0, which means that the acceleration is equal to 0. Nothing's accelerating, okay? Now that doesn't mean that nothing's moving, but if they're moving, they have to be moving at a constant velocity.
Right.
So we're going to consider 3 problems here in statics. They all involve a mass being suspended from some kind of wire or string or rope or whatever you want to call it. So let's look at the first one, right? Here we just have a mass suspended from, say, the ceiling by some rope.
Okay.
Now, the first thing that we do in problems like this is isolate the system that we're interested in. And in this case, it's the mass. So we draw a nice diagram. Let me do it like this, maybe. And we have to indicate where all the forces are. And I'm going to do it like this. This is a mass M. So the first component is its weight, which is equal to the mass of the body, M, times the acceleration due to gravity.
Alright.
And then we have a tension. That's from the rope or the string or the chain or whatever you want to consider it to be. And that's pulling upward on the mass. Okay, maybe this is a picture. Maybe it's a heavy block. Maybe it's an engine. Who knows? So now that we've got a nice picture, we need to put in a coordinate system, right? So let's put in an XY coordinate system with X in this direction and Y in that direction. So that, of course, makes the weight a negative vector because it's acting in the downward direction, whereas the tension is acting in the upwards direction. Now, you'll notice that there don't seem to be any forces in the X direction. So that makes this a particularly easy problem to solve. So for us, in this case, the sum of the external forces is just going to be the sum of the external forces in the Y direction.
Okay.
And so let's enumerate those now. We're going to have the tension plus the weight, and that is going to be equal to 0 because this is a statics problem. There's no acceleration. And so that means that the tension is equal to minus the weight. But the weight we said was equal to minus mg, which means that the tension is equal to a negative times a negative is positive, m times g. I guess I could catalog that result over here. Makes sense? Pretty straightforward, right?
Yeah.
Okay, that's the first case. Now let's do the second case. As much change, you'll notice that in this case we have 2 ropes suspending this mass. And let me just point out that they are symmetrical about the center of this mass. I'm going to assume that the mass is equal. It's not some weird mass. It's like heavier on one side than the other. We'll assume it has a uniform mass. And if you wanted to, you could even consider those 2 ropes pulling from the same point, but that's conceptually difficult. So we'll just assume that they're separated symmetrically about the center of this thing, but very close together. So we need to draw the free body diagram, right? So we isolate the system again. We're just talking about the mass here, right? So we're going to look at that. And we've got a tension force 1 and a tension force 2 pulling in the upward direction. And we have the weight of the object pulling in the downward direction, right? And that again will be equal to mg. I'll use the same xy coordinate system, so that will be minus mg. And so this time, again, there are no forces in the x direction, so that makes life easy. But in the y direction, we again find that the sum of the forces this time will be T1 plus T2 is equal to plus the weight will be equal to 0 since it's a statics problem. which means that T1 plus T2 equals minus W, which of course is equal to positive mg, just like before. The difference, though, is that this time we have two tensions adding together. And the question is, well, how is the weight distributed over these two, lines, these two ropes? Is it equal? If it was equal, that would mean that, T1 could be half an mg and T2 would be another half an mg. So half an mg plus half an mg is, full mg, right? And I would argue at this point that by symmetry, right, it should be equally distributed, okay?
Okay.
So I would say that T1 equals T2, which equals 1/2 mg by symmetry. So now let's look at the most difficult. I'm going to assume that in all of these problems that our XY coordinate system is kind of the standard one like this. That's to the right is the positive X direction, and up is the positive Y direction. Let's look at the third example. So this time we have to isolate the system. And so we're going to isolate the system. We call it M. We'll again have the weight in the downward direction, but now we have these different tensions. But this line here, the one that makes a 30-degree angle to the ceiling, right? This I'm going to call T1. And note that we can break this into its component form as follows. Here I have T1 in the X direction, and here I have T1 in the Y direction, right? This angle, so since it makes a 30-degree angle here, this is an alternate interior angle, so this is also 30 degrees, you see?
Yeah.
So T1 in the X direction is going to be equal to, notice it's in the positive direction, so T1 times, anybody? Cosine or sine to get the X component of this tension?
Cosine.
Yeah, T1 times the cosine of 30 degrees. And in the Y direction, this tension in the Y direction, right, will be T1. Notice going in the positive direction, you can kind of see that, right?
Yes.
Times the sine of 30 degrees. But over here, right, we have T2, right? I'm going to draw a little arrow indicating that this is T2 in the X direction, and that's going to be, what's the angle here? Well, this angle was 60 degrees, right? Because the angle to the ceiling is 60 degrees, which means this alternate interior angle is also 60 degrees, right?
Yes.
So I have to put that into my three-body diagram. And so that makes T2 in the X direction equal to, that's a terrible equal sign. I'm trying to make this bigger, but T2 in the X direction is equal to, this time notice that the force is going in the negative direction. So let's go ahead and reflect that in the sign of this by putting negative T2, right, times the cosine of 60 degrees. The Y component, however, is in the positive direction still, right? So T2Y is equal to positive T2 times the sine of 60 degrees. Now that I have all those components in, I'm ready to solve this thing. So using Newton's second law, this time, since we have contributions in the X and in the Y, we're going to consider the sum of the forces in the X and the sum of the forces in the Y direction separately. So the sum of the forces in the X direction will be equal to, well, we've got T1X, right, plus T2X, right? Those are the only two forces in the X direction. We've got the X component of the tension from tension 1 and the X component of the tension from tension 2, right?
Yes.
But we've already kind of calculated what those are, and so T1X is equal to T1 times the cosine of 30 degrees, right? And then T2X is minus T2 times the cosine of 60 degrees. And that we know is going to be equal to 0, because this is a statics problem. We're assuming that there's no acceleration in the X direction or in the Y direction.
Okay.
And so this gives us a, kind of a handy relationship. If we algebraically move, T2 over here, we'll end up getting that T1 is equal to the ratio of the cosine of 60 degrees divided by the cosine of 30 degrees times T2. The sum of the forces in the Y direction, well, we've got the Y component of the tension from 1, so that's T1Y, plus the Y component of tension 2, and then plus the weight will be equal to 0. And we have something for those values. We have the T1 y is equal to t1 times the sine of 30 degrees plus t2y is t2 times the sine of 60 degrees. And then the weight is minus mg. And so this will be equal to mg, right? If I just add to both sides, right?
Mm-hmm.
And then we can just algebraically replace t2 or t1 if we want with this algebraic expression, right? So we can substitute in for this, right? So we would get that t1, which is, that's the cosine of 60 degrees divided by the cosine of 30 degrees times the sine of 30 degrees times t2 plus t2 times the sine of 60 degrees is equal to m times g, right? So there's a lot of stuff going on here. So now I guess we need to actually evaluate what these expressions are so that we can solve for t2 here. We're kind of running out of room too.
Mm-hmm.
So let's move over here. So let's just write down right here that the cosine of 30 degrees, which will also be equal to the sine of 60 degrees, as you remember, is equal to square root of 3 over 2. Is that right?
Wait, yes, that's right.
And then the cosine of 60 degrees will be equal to the sine of 30 degrees, which is equal to 1/2. Yes?
Yes.
Now let's rewrite this expression, t1 sine 30. Well, the sine of 30 is 1/2, so that's 1/2 t1 plus t2 sine 60. Sine 60 is square root of 3 over 2. So that's square root of 3 over 2 t2 equals mg.
All right.
And then let's substitute in for t1 equals the cosine of 60 over the cosine of 30 t2. So t1 will equal the cosine of 60 degrees is 1/2, right? So that's 1/2. Divided by the cosine of 30 is square root of 3 over 2. Well, that's the same thing as multiplying by 2 over the square root of 3. Canceling those 2's out, times t2, right?
Yes.
So 1/2 times this, right? That's 1 over the square root of 3 t2 plus the square root of 3 over 2 t2 equals mg.
Yes.
Multiply both sides by 2 square root of 3. That gives me 2 square root of 3 mg over here. Gives me t2 here plus 3 t2 here, right? 1 plus 3 is 4 t2. So I get 4 t2 equals 2 square root of 3 mg, which means that t2 is equal to square root of 3 over 2 m times g. Now t1 then is just equal to 1 over the square root of 3 times t2. So that means that t1 is just equal to 1/2 mg. So now we've got the tensions for this one. t1 is equal to mg over 2, and t2, the tension in the second line, is equal to the square root of 3 over 2 times mg. So I'll write this as 1/2 times mg. Yeah. So, 3 statics problems. That's how we solve them. The last one obviously being the most complicated one because there's some trigonometry there, but you know it's not that bad in the end. I could have made it a little simpler by substituting in for these cosines and sines earlier on, I think. Yeah, I think that's it. Does that make sense?
Yes.
Okay. Okay, lecture 34 is on dynamics. So last time we talked about statics. That's where the acceleration of the system is 0. This time we're going to consider the opposite, the other situation where the acceleration is not 0. Let's start with the following. Imagine that we're in an elevator and we're standing on a scale. Now, what are the forces involved here? Let's do a free body diagram. And we're going to do it on the person, okay? But I'm going to represent the person with just a block of mass m. Well, there will be the weight from gravity, which is pulling down. But we'll also have a normal force acting in the opposite direction. And that's the force of the floor, or the scale in this case, pushing up on us.
Okay.
Now, in fact, it will be, as we're about to find out, this is a statics problem because the acceleration is 0, right?
Yeah.
So this is a non-moving elevator, or maybe it's moving at a constant velocity. It doesn't matter.
Okay.
But the acceleration is 0. So the x direction doesn't matter here. We'll say that the y direction positive is up, which means this weight will be in the negative direction. And so the sum of the forces in the y direction will be equal to n plus W, which will equal 0 because the acceleration is 0. So this means that N is equal to minus W. The W is minus mg, right?
Yeah.
That would be the force of gravity, right? So if we didn't have the scale under our feet and the elevator under that, then we would just be falling. And we know that that would be mg in the negative direction. So this is equal to the negative of a negative is positive, and so that's mg. Okay, so this normal force is the weight that you would read on your scale.
All right.
So if you were, 100 pounds, and this is going to be somewhere in the neighborhood of 400 newtons. Now let's consider the case where it's accelerating. So no longer is the acceleration equal to 0. The free body diagram will be the same. We'll have a normal force balancing out with the weight.
Okay.
But it's not going to balance out because I said it's accelerating. So this time, the sum of the forces, which are the same, right, will have N plus W equals M times A. So there's some acceleration. So in this case, we said that the acceleration is less than 0. So that means that this is in the negative direction. So we'll say minus MA.
Okay.
So you can see, you're going down with some acceleration. So now what does the scale read? What do you think the scale might read? Is it going to be less or greater than or the same as what the scale read when we were sitting still in the elevator? What do you think?
Greater than this?
All right, we got two different answers. We got one that says greater than, one that says less than.
I'll go greater than. Yeah, me too.
So you think the scale will read a bit. So if I weighed 100 pounds when the elevator is standing still or moving with a constant velocity, then you think that if it's accelerating downwards, right? So I'm going down, maybe on the 100th floor, and now I'm going to go down to the ground floor. So the elevator will accelerate downwards, and you think the scale is going to increase the weight that I see on it. Is that right?
Yeah.
No. See, when you start to think about this, then you kind of start to see the answer, right? We need to let our intuition guide us in these kind of things, okay?
Okay.
So what do you think is going to happen to the scale? Now imagine that instead of standing on a scale, I was standing on you, right? As the elevator starts to go down, accelerate down, right? I want to move down with a constant velocity. I want to accelerate down, okay?
Yeah.
Do you think that you would feel the weight on your stomach increase or decrease as that accelerator starts to go down?
Decrease.
You think both? Okay, so you really don't know, huh?
Yeah.
If I'm riding in a car and I hit the accelerator, right? Do I get slammed back into my chair or do I get shoved forward?
You get slammed back into your chair.
Okay, so now the car is the elevator and we're going down. We're accelerating down. So which way am I going to feel pushed? Up towards the top of the elevator or down towards the bottom of the elevator?
I mean,
Okay, so if I'm being pushed up some, what happens to the scale?
lighter.
It's going to read a lighter weight, right?
Yeah. Yes.
So our weight, again, is minus mg, so I have that N minus mg equals minus ma, and I can solve for N, because remember, this normal force, that's the force of the scale pushing on me. Through Newton's third law, the force that it feels pushing on it will be equal and opposite to this force, right? So N, the normal force, really is what I'm going to read on my scale. So I solve for N, right? That will give me that N is equal to m times g minus a.
Okay.
So the usual acceleration due to gravity, right, it will be less than that. And so the force that I'm pushing with on the scale will be lighter, right? So does this make sense? Before, when we stand on it, it was mg. Now we're mg minus a, right?
Yes.
So we can see that this one is less than this one.
Okay.
Well, let's consider the other situation. Now we're accelerating upwards. So maybe I'm on the ground floor, and I push the button on the elevator, and I shoot up towards the top. But unlike most elevators, let's assume that this elevator has some constant acceleration that it applies to us as we ride up.
Okay.
So what do you think is going to happen here this time? Is the scale going to read the same, or is it going to be less than like it was when we were accelerating downwards, or is it going to be more because I'm accelerating upwards? Again, think about someone standing on your stomach, right, on an elevator, and then the elevator, like a rocket, shoots up, right? Do you feel more pushing on your stomach as you're accelerating up, or less?
More?
Yeah, more, right? Just like in the car, right? This is the case of the car. So I'm at the bottom of the elevator in my car, and I'm going to drive up the wall, right? But I've got a really good car that can drive up walls, and if I hit the gas, I'm going to feel like I'm pushed back into my seat, right?
Yes.
So let's write, again, the free body diagram is the same. It's just this time, instead of being equal to 0 or being equal to minus ma, the sum of the forces will be equal to plus ma, because I said that the acceleration is now greater than 0. It's positive. So what happens this time? Well, we still have n minus mg equals ma, and I solve for n again, and I get n equals m times g plus a. Because it's adding to the acceleration due to gravity,
Yeah.
we're going to be greater than we were when we were sitting still.
Yes.
So we can summarize these results in the normal force when a is less than 0 is less than the normal force when a is equal to 0, which is less than the normal force when a is greater than 0.
Okay.
Okay, so does everyone understand the elevator examples we've done here?
I think so.
And it's dynamics because the acceleration is no longer 0. So in the statics problems, we always wrote Newton's law and we set it equal to 0, right? Now we have to set it equal to the mass of the system times the acceleration that we experience.
All right.
Okay, so lecture 35 is on Atwood's machine, which I've drawn a small picture of here. We're not actually going to solve this. This is in your problem sets, but I'm going to give you hints on how to solve it. But let me state what the Atwood's machine is all about. This is a device that was originally used, I think, to measure gravity, okay, what the gravitational acceleration is.
I was used to spin wood.
No, and so what it is, it's basically two masses, not necessarily equal. They're usually different. Otherwise, you would get no acceleration. And they're connected by a piece of unstretchable rope, right? You're going to get the least stretchy rope that you can get. And it's wrapped around a pulley. And so you can see physically what's going to happen, right? If M2 is greater than M1, right, then you're going to accelerate. This will accelerate downward. This guy will accelerate upward. If the weights are pretty close to each other, the acceleration will be rather small. And that's where the advantage comes in. It's a little bit like what Galileo did with his inclined planes, right? He slowed gravity down so he could make more careful measurements.
Yeah.
And so you're doing the same thing here. You're kind of slowing down gravity, okay? But you're going to be able to figure out what it is. So you measure these accelerations, and that will help you figure out what the gravitational acceleration is. And that was the purpose behind it. But again, we're not going to solve this problem. Instead, what we're going to solve is a related problem. And this should give you some insight into how we will solve the Atwood's problem, Atwood's machine problem. I don't remember what year it was built, but it's George Atwood, I think, is the builder of the machine. It's probably 1780 or something like that. So here's the problem we're going to solve. Put a pulley here. There we go. So let's assume that this is a frictionless table, okay? And what we've done is we've rigged up a pulley system, right, like this, since we've connected this mass M1 to this mass M2.
Yes.
And just like with Atwood's machine, we have a line which we'll assume is not, you can't stretch it, so it's not elastic, and we'll assume that its mass is negligible, so it doesn't contribute anything to the problem, right? Because remember, if it did have mass, then the tension that you would feel here and here would be different. But if the mass is negligible or 0, then we can assume that the tension 1 felt by body 1 and tension 2 felt by body 2 are equal and opposite, okay, just like they are here.
Yeah.
So another thing that we'll have to take into consideration in order to solve this problem is the fact that the acceleration of body 1 is related to the acceleration of body 2, right? You can see it. And the same thing with Atwood's machine, right? If M2 is accelerating downward very quickly, then mass 1 will be accelerating upward at the same rate. And the same thing in this problem here, okay? So this is like Atwood's machine light, which is why I'm going to work this one out, and I will leave Atwood's machine for you to solve, because there's not that many of these dynamics problems that I can come up with that are interesting, and this is probably one of the more interesting ones that's not overly burdened with complexities. Let's write our assumptions down for starters. I'm going to assume the magnitude of T1 is equal to the magnitude of T2, which is equal to some scalar value T.
Okay.
And the acceleration of 1, which will be in this direction, right, is the magnitude of that will be equal to the magnitude of the acceleration of 2, which we will just call A.
Yeah.
Make sense?
Yes.
So these are what we call constraints on the system, and that if we didn't have these constraints, then this would be unsolvable.
Okay.
So I think the first thing I'd like to do is let's deal with, and we're going to call this our x direction, and this our y direction. That's a terrible x. So this is the positive x direction. This is the negative y direction.
Okay.
We have two bodies here, right? And a free body diagram requires us to isolate one of these bodies. So we want to consider the system. We've got to isolate each body one at a time. So we'll say, for body 1, Okay, that's this guy here. Let's draw a free body diagram for it. Well, we have the normal force and weight. They're completely canceling each other out, right? It's a balanced force. There's no acceleration in the y direction for body 1, right?
Yeah.
So the sum of the forces of body 1 in the y direction is equal to 0. What about in the x direction? Well, here, the sum of the forces in the x direction, right, will be equal to the mass of 1 times the acceleration of 1. Now here we're going to, because it will be accelerating in this direction, we know that that's positive.
Okay.
So it's equal to ma. Now what is the sum of the forces acting on this body? Well, there's really only one. That's the tension, right? Also acting in the positive direction. So here we have that the tension is equal to m1a. Now let's look at body 2. This time, again, we have a weight and we have a tension, T, right? Now in the x direction, there are no forces in the x direction. So there's no acceleration in the x direction, so we'll have a 0 equals 0 kind of thing. So I'm not going to write anything down for that. But in the y direction, right, the sum of the forces in the y direction for body 2, right, this is m2, oops, m2, this would be m1, will be equal to the mass of body 2 times the acceleration, but this will be in the negative direction, right, because it will be going downwards, yes?
Yes. Yeah.
Do you think it's possible to set up a contraption like this where the acceleration is going up?
Yes.
How would we do that? Any answers on that? Well, I can imagine if somebody pulled on this, right? If they applied a pulling force to M1, then you could cause M2 to accelerate upwards, right? But there's no set of masses that I can choose that would cause M2 to accelerate upwards. We're assuming this is a frictionless surface, okay?
Okay.
So if we chose, really heavy M1, would that cause M2 to accelerate upwards? No, it would not, right?
It would make everything stay.
No, it wouldn't balance it out. There's no friction. So M2 will still feel an acceleration due to gravity downwards. Now with friction, yes, right, you could cause M2 not to move. You just have to make sure that the frictional force, which we haven't gotten into yet, was big enough to keep M1 from moving at all. But M1 will always feel a pull in that direction, right?
Yeah.
As long as there's a mass here. Doesn't matter if it's less than or greater than or equal to the mass, it's going to feel a pull. And on a frictionless surface, that means it will always accelerate to the right.
Okay, yeah.
Yeah, the only way you could get it for M2 to accelerate upwards is if somebody pulled on this on M1 that way.
All right.
So it's different than Atwood's machine. Atwood's machine, the direction of the acceleration will be determined by which one is greater, M1 or M2.
Okay.
Or if they're equal, there will be no acceleration. Okay, so we've got that the sum of forces in the y direction for body 2 is equal to minus m2a. Now we have to enumerate these forces, and what do we have? We'll have a tension, T, which is in the positive direction, plus the weight, which will equal minus m2 times a. The weight, of course, is minus mg. So this becomes T minus mg, where m is m2, equals minus m2a. Now how do we solve for these things? Well, here's the trick, and this will help you out with Atwood's machine. If I take this equation from body 2, and I subtract it from this equation for body 1, right? Let's solve for the tension in this equation. So this one would say that the tension T is equal to m2g minus m2a. And so if I add that to, we'll call this equation 1, and we'll call this equation 2. And so 1 minus 2, what does that give us? That gives us T equals m1a, and T equals m2g minus m2a. If I subtract these, right, T minus T, that'll be minus this. So minus this, minus this. Minus a minus is a plus, right? So I get T minus T is 0. M1A minus M2G is, well, really it's M1A plus M2A minus M2G. I should have collected like terms, right? So move this over here, right? And this will just have a 0, right? So we have M1A plus M2A. Well, that's just M1 plus M2 times A. And here we have minus M2G, right? And that's equal to 0. And so I can solve for acceleration A. First, I'll move M2G over to the other side of the equation, and I'll get that A, the acceleration, is equal to M2G divided by m1 plus m2.
Okay.
So that's the acceleration, and then I'll move the g outside. So you see it's this ratio of the mass m2 to the total mass, m1 plus m2. Sorry, this one here. So that's the acceleration that we'll get. It's the ratio of m2 to the total mass, m1 plus m2.
Okay.
And so if, for example, what if m1 was really light? What if m1 was basically 0? What would we expect? Let's say that there is no m1, right?
Yes.
What do we expect m2 to do? We expect it to just fall, right?
Yes.
So if m1 is 0, we get m2 over m2. Well, that just cancels out, right? That's just 1. So we get the acceleration is equal to g.
Okay.
So that makes sense, right?
Yes.
What else could we do here? We could consider the case where m2 was very, very heavy, and that would basically give us the same thing, right? We completely ignore m1, because if m2 was very large, right, then what would we say? We'd say the acceleration is equal to m2, which is a really large number, over m1 plus m2 times g. But if m1 plus m2, if m2 is very, very big, that's basically saying m1 is 0 again. And so this is just approximately m2 again, right?
Yes.
And so for very massive m2, it just behaves like it's free falling, right?
All right.
I suppose you could have the other case where you had a very heavy m1 and a very light m2. We don't want to make it 0, because if we made it 0, that would say there's no acceleration, and that would be like, well, if it's 0, there's nothing to fall, so there is no downward acceleration. But let's let m1 be very big, much, much greater than m2, right? What's the acceleration going to look like? Well, m1 plus m2, since m2 is very small compared to m1, this will be like approximately m2 over m1. So we have a very small number over a very big number times g, right?
Yeah.
So we'll have a very small acceleration. So if I have this, a very heavy object, and this is a very small object, even though there's no friction, then the acceleration downward will be very slow.
Okay.
We're not done yet, though. We got the acceleration. There's one other thing that you'll need to be able to solve for to get the tensions in the Atwood machine, right? What's the tension in the line? Well, you could, for example, instead of subtracting these, add these.
Okay.
And that you could solve for the tension in that case. The problem is that you're going to have a quadratic equation to solve, and that's going to be a pain. My suggestion is that once you have the acceleration, let's just use it in the easiest of these two equations that we can find to find out what the tension is, because we could either use this equation, equation 2, tension is equal to m2g minus m2a, right? Or we could use it in equation 1 and see what the tension is equal to. Let's do it in equation 1. That looks easy. So from equation 1, we get, and we'll call this equation 3. So 1 and 3 gives me that the tension T is equal to m1 times A. But A is just m2 over m1 plus m2 times g, right? So that gives me m1, m2 divided by m1 plus m2 times g.
Okay.
And that will be the tension that we have.
Okay.
And so you can use the same strategies that I used here to solve the Atwood machine in a pretty straightforward manner. I don't think it's that much harder, but you could consider this a warm-up question.
Okay.
All right? So that's the Atwood's machine.